Start. Okay, welcome to this colloquium before the Easter break. First of all, a disclaimer for people online. We have internet issues today, so be patient should the connection drop because we are connected using the cell phone as a hotspot. So if Fabio gets a call, the hotspot is broken. So we will get back to you here at convenience. So it's a pleasure to have today with us Benjamin Magnelli from Paris-Saclay. Welcome to Bologna.
And just by my name, I'm not Italian.
And he's not Italian. French is based at CA in Saclay, and he's an expert in galaxy evolution, in particular in studying the build-up and evolution of star-forming galaxies across the universe, in particular using inference submillimeter data. So studying, characterizing their properties such as the gas and dust content, mass, temperature, spatial distribution, star formation rate, and the star formation rate density up to high redshift. Using first Spitzer and Herschel, which he started with during his PhD, which he got in 2009 at the CA, with David Elbaz and also Shari. And then in 2012, he moved to MPE in Garching, working in Rainer Genzel's group for 3 years. And then, in 2012, he finished his 3 years period in MPE. And in 2012, he moved to Bonn at the Max Planck Institute for Radio Astronomy in Frank Bertoldi's research group, where he spent 8 years. And he got deep knowledge also of radio observations and interferometry, also working with ALMA. He's one of the co-leaders of the A3 Cosmos and A3 Goods project to use archival ALMA data mining, which they make commensal to the scientific community. And recently, he's been also involved in the JWST MIRI and also Euclid data. And today, he will tell us about the universality of star formation across cosmic time as seen by inference submillimeter telescopes. Thank you, Benjamin.
Thanks a lot, Ivan. It's a real pleasure to be here. So today I will basically base my talk on the talk that I gave a few months ago, because in France I passed an exam that you have to do to become full professor, which we call the habilitation. And so this talk will basically not be on a very specific topic that I've been working in the last year, but more an overview of the field that I've been working, that is galaxy evolution, and what we learn over the 10, 20 years on this thing. So I will try to show you an overview of this. Okay, so as Ivan said, I mean, I've been working on galaxy evolution, and galaxy evolution is a very vast and fascinating topic for sure. It is also a very complex one because it involves understanding a lot of very complex physical mechanisms that basically take place in various time scales. So we want to understand the formation of the very first galaxy about 200 to 300 million years after the Big Bang, to understand how they reorganize the universe. And of course, we want to understand how they evolved over the last 13 billion years up to the great zoo of galaxies that you observe in the local universe, from this beautiful blue spiral galaxy up to the very red and dead ellipticals. And of course, that's also involved understanding how galaxies evolve into the large-scale structure of the universe. So that's involved understanding the formation of this large-scale structure, how you form the galaxy, and up to the formation of the very stars. So it's a very complicated problem to solve, and making an analogy with the simulation, you can use an observational point of view 2 different approaches. So what I will call the bottom-up approach, where you will study in details few systems and try to understand at all scales what are the mechanisms in place, to understand the feedback of stars, the feedback of AGN, the dynamics of 1 or 2 systems, and then you try to build up your knowledge about the full universe by going to larger scale. Or you can have like a top-bottom approach, where you try to have a very statistical approach of the universe and try to understand the key parameters that drive galaxy evolution. And in a sense, try to do principal decomposition analysis of galaxy evolution. And that's more or less the approach that I will try to describe, that we have been following for many years, is to try to have to decompose this very complex approach in a very simple way. And first try to understand what are the key parameters that drive galaxy evolution, and then go step by step to more and more complex understanding of this history. Okay, so what you want to do, if you want to do that, the first thing you want to analyze, when does galaxy evolution take place? And this simple question is, of course, very important to answer. And what you want to do is simply to measure the star formation rate density, so the amount of total stars formed by the universe in a given cosmology volume. So it's a very simple question that you want to assess, but of course, it's quite difficult observationally to answer. So the first thing is that, of course, what you want is to measure the emission directly from the stars, these newborn stars. And usually we are lucky because massive stars do not live very long and emit mostly the prime emitter of UV radiation. So if you measure the UV radiation, you can get the star formation rate of these galaxies. And it's quite nice because we have actually a very nice view of the red-stream UV universe. Actually, it's easier to do the very high redshift universe with James Webb than to do the local universe because we don't have really a lot of UV facilities. We have galaxies, but so in a sense, it's relatively easy to do it in the UV. We use Hubble up to this redshift, and now you can extend it even up to the redshift 10, 11, 12 to see the UV photon. But as you know, I mean, these stars have been formed from cocoon of gas, and usually this gas is coupled with the dust. And so a lot of this UV radiation is actually absorbed by the dust and re-emitted in form of thermal emission in the infrared. And so if you want to have the complete budget of star formation activities, it's clear that you need to look at the infrared. Whether or not it's important, we didn't know much. IRAS was telling you that in the local universe for some galaxy, it was extremely important because you will not be able to measure their total star formation rate uniquely from the UV. And so with Spitzer and Herschel, of course, we have been able to really unfold the star formation rate density of the universe up to redshift of 3 and 4 with many of the work that we have been doing with Herschel. I mean, Carlotta and I have been doing quite a lot of work on this topic. And when you do that, you realize that actually, if you don't take into account the infrared, you miss a lot. So about only 10 to 20% is seen directly in the UV, and most of it is a dust to obscure star formation rate. And you can try to correct the UV from dust attenuation, but you will have a large uncertainties because, of course, you have to correct by a factor 10. So any small uncertainties will propagate enormously. Now, if you combine this, you have probably one of the most famous plots in galaxy evolution that was published, taking all this data together by Maddow and Dickinson in 2014. And so what you learn from that is when galaxy evolution happened. So you can see that the universe is really not boring. I mean, it's evolving, it's dynamic, and in a sense. And so you have a huge increase of the star formation rate density of the universe from early epoch up to what we call cosmic noon, which is basically 3 gigayears after the Big Bang. And since over the last 10 gigayears, you have a smooth decrease by a factor of 10 to 20 of the star formation rate density of the universe. And this right away tells you that about 50% of the stars in the local universe have been formed actually at high redshift. So even though it's nice to study high redshift galaxy, but it's not only nice, it's necessary. So if you want to understand galaxy evolution, you cannot just look at the local universe. It's of course important. You can do resolve observation. You can understand nicely the mechanism at play. But if this mechanism totally change at high redshift, then you will miss most of how galaxy have assembled their stellar mass if the star formation activities is driven by different mechanisms at high redshift. Now, of course, that's raised a lot of questions: is why does it increase and decrease, and what drives this star formation history? And one simple thing that you could do is to say, okay, maybe at high redshift the universe is much more efficient in forming stars. So when you give a given amount of molecular gas to the universe at z = 2, it will be more efficient into turning this molecular gas into stars. Or you could think, okay, maybe at z = 2, the universe a higher fraction of the baryon is actually already in the molecular phase in the high redshift universe, and that's what explains this rise and fall of the star formation history. So in a sense, you say, okay, if I would be able to do the same plot and measure the molecular gas mass density of the universe that we can observe, if you see something that goes up and down, that means that it's really the molecular gas content of the universe that drives this star formation history. Or if you see something that is flat, maybe something like that, that means that the universe at high redshift have a higher star formation efficiency. So of course, this kind of measurement are difficult to obtain because you need to go with ALMA, measure the CO line, or measure the dust mass in galaxies and then compare that in molecular gas. But we have been doing that, and especially with a program where Roberto De Cali was highly involved with what we call the aspects. So that was one of the first large programs with ALMA to do very deep observation, basically in the Hubble Deep Field. And even though we had large uncertainties, what we see is that the molecular gas mass density measured by CO by the dust-based proxy is indeed seems to follow quite nicely the star formation rate density of the universe that is shown here in the black line. So even though we have large uncertainties, that seems to say, okay, the star formation efficiency at high redshift is more or less the same than in the local universe, pointing towards kind of a universal mode of star formation in the universe. Of course, this very demographic and statistic approach tell you a lot, but what you want is to gain more complexity. So the natural thing is, after having looked at this axis, so the redshift or the look back time, what is the effect on the galaxy evolution, is to look at a given redshift, how, for example, the stellar mass, which is linked to the gravitational well of a galaxy, drive the star formation. So how star formation in a given galaxy relate to its stellar mass. And so here is a plot at z equals 0, where I plot the distribution of galaxies, every galaxies. And what you can see is the bimodality. So you see like this, a very massive galaxy with basically no star formation. And then you see star forming galaxy that align on a nice correlation between the star formation rate and the stellar mass of galaxies that have been dubbed right from the beginning, basically in 2007, what we call the main sequence of star forming galaxies. So this is not really totally new because, of course, the star formation rate stellar mass plane is simply a reprojection of the color magnitude diagram that is well known for decades, where you have your blue cloud here that are not very bright because they are not so massive, and they are blue because they are star forming. And then you have your red cloud that is brighter because they are more massive, and they are red because they are non-star forming. But what is nice in this star formation and stellar mass plane is that this physically motivated reprojection allow you to try to make sense of the slope of this main sequence correlation, which has a slope that is more or less linear, but I will go back to that later. But most importantly, what is very striking is the tightness of this correlation. Because if you give me the stellar mass of a local galaxy, and I can tell you what is the star formation activity within a factor 2. And that tells you something fundamental into its mode of star formation. So what we interpret this is that it's kind of a proof that in the local universe, most of the galaxies are in what we call a secular mode of star formation. And what it means that its star formation history over the last gigayears is relatively smooth and constant. Because any huge and significant stochasticity in the star formation history of galaxies population will basically broaden this correlation or even make it disappear. Okay. So in a sense, that means most of the galaxy, and we know that the Milky Way sits right on the main sequence, indeed, at the star formation history that over the last few hundred to gigayears is relatively constant. Okay. So in the local universe, most of the galaxy, as we know, are more in this secular mode of star formation. You have some starbursts like R220, but they don't seem to dominate the star forming budget of the universe. So what happened at higher redshift? And now I show you some example where you can look at this correlation. And now we have better constraint even up to the redshift of 4. That up to redshift of 4, you see a nice correlation. So this main sequence of star forming galaxy exists. That means there is a correlation, but also there is still a very tight dispersion of about a factor 2 around this average. And so that means that at high redshift, when you see this kind of thing, that galaxy at a redshift of 2 seems still to be dominated by a secular mode of star formation. And that was surprising because at the time, in 2010, we were thinking that the high redshift universe is dominated by Lyrics or Euclids, which have star formation that is about 10 to 100 times higher than the local universe. And in the local universe, those galaxies are associated with merger, and so star bursting activities. But it seems that based on this, it's not the case. And the only thing that changed that indeed the galaxy at high redshift are forming 10 times more stars at a given mass than the local universe, but they still follow this nice correlation and seems to be in this secular mode of star formation. So if you make the math, about 80% of the present day stars have been formed in this relatively universal secular mode of star formation activities. And of course, the question is, what about starbursts? So starbursts, what is nice with this definition of this main sequence, that by definition, starbursts must be located above this main sequence. Because the original definition of starburst, like up to 20, is that the instantaneous star formation is a factor of 2, 3, 4 higher than the average star formation of this galaxy over the last few 100 million years. So it's difficult to measure this average star formation over the last 100 or 500 million years. But what is nice with the main sequence, you don't need to do it in an individual fashion, because by definition, the average star formation of a galaxy of a given mass at a given redshift must be close to the main sequence value, because the main sequence is telling you most of the galaxies are lying within a factor 2 of this value. So of course, that seems to point toward this universal mode of secular mode of star formation activities up to the very high redshift, but it's just based on the fact that there is a correlation and that it has a small dispersion. So it's maybe not enough to confirm that. So then many studies have been done to try to confirm that indeed high redshift galaxies are forming 10 times more stars, but basically have the same properties, physical properties, than galaxies that are on the main sequence at low redshift. And so I cannot show, because I mean there are tens and tens of studies about that, and I would say now most of the high redshift studies will always put their galaxy in the context of where do they locate compared to the main sequence. And so I will show two results that I think are very striking. So here is in 2011 with Steinwit, we look at the morphology of the light profile in the optical of galaxies. And what we plot is the Cersei index of these galaxies. So the average Cersei index or the median Cersei index of galaxy with a given star formation rate and stellar mass. And you don't care if it exists a main sequence or not, you just plot what you see. And you can clearly see that the main sequence appear very nicely. And you can even overplot where is the main sequence, and you can see that it's clear that main sequence galaxy, even at high redshift, even if they have 10 times higher star formation activities, they don't look like natural merger, disturbed morphology. They have disk-like morphology, so a Cersei index of 1. And on the other side, you have like this bimodality. So you indeed refound that this massive non-star forming are bulge-like. And you can even see that if you go above the main sequence, you have a change again of the light profile that could be associated with a different mode of star formation, associated with merger, likely, but it's still to be verified. Now, the second study, of course, I have to show some of my results. So this is a study that I did with Herschel when we had like a nice Pax and Herschel and Spire observation. We could determine the dust temperature of galaxies. So we need to do some stacking and things like that. But here I show, of course, the best redshift bin and so on and so forth. But here is the same thing. I just plot the median or the mean dust temperature of a galaxy in a given location of the main sequence. And I don't care if there is a main sequence, I just do like this. And you can clearly see that the main sequence appear nicely. Okay, so the ISO temperature is not following a given star formation rate, but really the location of the main sequence. And it's very important because the dust temperature is telling you something about the condition of the ISM that give rise to the star formation activities. And in a sense, it's related to the star formation efficiency of galaxy. And so it's surprising that galaxies that have a star formation rate that vary by increase by a factor 10 here, but if you go to the highest redshift, you also find the same dust temperature for main sequence, that they have the same ISM condition. And so in a sense, the way we interpret that is that they have more or less the same star formation efficiency, most likely. And also the fact that a galaxy at higher stellar mass, at higher redshift, is kind of just the assembly of, kind of a universal brick. So if you have 10 times more star formation in the more massive galaxies, that's because you have 10 times more similar star forming region. But in a sense, they don't change. Each individually, they have the same star formation efficiency, and so on and so forth. On the contrary, you can clearly see that things that are above the main sequence have hotter dust temperature and therefore higher, most likely higher star formation efficiency. So they are indeed in a different mode of star formation. So that is good, but it's just the dust temperature, and what we really want is really to measure the molecular gas, okay? to look at the cold gas content, either from CO or from a Rayleigh Jean observation, and that you can only do that with ALMA. Unfortunately, all the studies that I showed you before here, I mean, I use tens of thousands of yes.
Yeah. Regarding those plots, besides morphology, you have information about the size of galaxies, for example, and fixed stellar mass.
Yeah, I will. Yeah,
okay.
I will go later. Yeah.
Fine.
But we have that. We have the mass size relation and things like that. And now we're exploring also the mass size of the star forming component, and that's what I'm doing with MIRI. And so what we wanted after that is really to look at the molecular gas, so from CO or from the Rayleigh Jean, that is a better tracer than the dust temperature because you have a degeneracy. So what we wanted is a lot of ALMA time, okay? Because we need 10,000 of galaxies. You cannot, I mean, it's all the things that I showed you are very statistical analysis. So if you look at few galaxies, you might be dominated by the dispersion around the relation and by small statistics. So we wanted thousands of hours of ALMA, and unfortunately, ALMA doesn't do that. But so we said, okay, so let's sit and relax. And because people are doing the job for us, they are observing with ALMA every time, and every cycle, a lot of people are looking at this very deep field, like Cosmos or Good South or UDS or whatever. Okay, and so they collect a lot of data at the phase center. There is a target that you can collectively and synergetically use for your thing. But of course, you have selection function problem, but you also have a lot of, not a huge area around this target that contain serendipitous detection, and not only serendipitous detection, but photons that have been captured by the detector that maybe didn't lead to detection, but we have been using a lot with Herschel what we call the stacking analysis, which is simply a cross correlation between position of galaxies that you know, to try to extract information for undetected galaxies that are individually undetected, but that collectively can be detected and give you an average measurement. So this is what we dubbed the F3 Cosmos project, and now it's, before it was only for Cosmos, but now it's from most of the extragalactic deep field. So we take everything from the archive and reduce it in a very homogeneous way. We do cataloging on this, we measure many of things, and then we release to the people. And now I think Sylvia has been updating now, and so you see, we start to have a lot of data. We have like about 3,300 detections, so it's quite a lot. And then we have more than 5,000 continuum images. And we still didn't look at the spectroscopic information because then you need, and that's the next step, maybe to develop machine learning algorithms to explore this huge data set. So what we could do with this is to, as I said, to develop stacking. So you do stacking in the UV space. So I mean, I will not go, but that allows you to have mean information or average information on a given population. And so with this method, the student Changming Wang did in 2022 and 2024, the first time really the gas content of a mass complete sample of galaxy up to redshift of 4. And so I don't know if you're familiar with the UV space, but not only we detect those galaxies, but we also spatially resolve them. Okay, they are not point source, so we can also look at the Schmidt-Kennicut relation and so on and so forth. So what we learn is that indeed the gas content of galaxy at any stellar mass that we explore strikingly increase as you go to higher redshift, and this increase basically match the increase of its star formation activities of galaxy. So that means that higher redshift galaxies are forming more stars because they contain more molecular gas. We don't need to invoke a new mode of star formation with higher star formation efficiency. And the second thing that is very important is that this gas reservoir at any given epoch that we measure are extremely short, small. So that means the depletion time, the time you will need to deplete this gas, this molecular gas reservoir, is of the order of 1 billion years in the local universe, and then about 500 million years in the high redshift universe. And that means that if you, and we know that the molecular gas reservoir, I mean, there is not a lot of H1 galaxy directly in this galaxy because the density means that most of the gas will be in the phase of the molecular gas. So that means that we know that these galaxies if you take the star forming population at z equal 2, and you let it run for 600 million years, that means at z equal 1.8, there is no more star forming galaxy. But we know it's not the case, because we know the main sequence is telling you have long duty cycle. And therefore, that's indirect proof that you need absolutely accretion of gas from the CGM or from the cosmic wave into this galaxy to sustain their star formation activity. And so this is what I call a new paradigm. I don't know if it's a bit too much to say that. But okay, so you have the star formation main sequence, and here you have your red cloud. And so if we put everything together, I mean, you have the tightness and the time independence of the shape of the main sequence that say that, okay, star formation history must happen over a long time scale. Okay, you might have stochasticity, but some are, you sustain over a few giga-years the star forming activity of this galaxy. And then you have very short molecular gas reservoir at any given epoch. So you need to have accretion of gas from the CGM or from the cosmic wave. And of course, if you speak to people doing simulation, they will tell you that you have accretion from the cosmic wave directly. And then you have like the same star formation efficiency, and therefore to understand the increase of the star formation rate density from redshift 0 to redshift 2, you basically have to invoke the fact that the tap that of the molecular or the baryon into the galaxy, of the gas accretion by the galaxy is increasing. So you increase the tap, and in reaction, you increase the star formation activity because the star formation efficiency remains the same. And that was put in a very nice way in what they call the gas regulator models, where in few differential equations, you can actually reproduce the location of the main sequence and the star formation history of the universe with only few equations. And with the main ingredient is what is the amount of gas that is accreted by a baryonic by a LO at a given epoch based on its LO mass. And this, from simulation, you can get it. And they basically show that it's worked nicely. And now there is further proof of this link between the tap from the universe, so how you open, how much you receive baryon. From the last student, Ivan and I were involved with Emmanuel Daddy, but also Paolo Professo have published this, that I said the main sequence is relatively linear, but actually is not totally true. But, so what we observed, that the main sequence at low redshift is linear, and then at a given mass, it starts to bend, okay, and become very flat. And this bending happens at higher and higher mass, and actually at the very high redshift, you barely see any bending, okay? And now if you map the bending mass of this galaxy to the theoretical halo mass onto which you can still accrete because you are not too massive. So if your halo is too massive, at some point, the thing that is supposed to accrete comes so fast that then there is a shock, and then the thing doesn't accrete anymore. Okay, that's the prediction from a theoretical, from the Decaying group and others. And this is basically this region. If you are here, you are too massive, you cannot accrete anymore. And if you translate those stellar mass into a halo mass, assuming more or less a factor of 10, okay, and then you end up with these black points that basically follow this region. So that's, of course, again, a very indirect proof, but it's surprising that indeed, if you take into account this, you can actually explain not only the location of the main sequence, but really the bending mass. Okay, so it's a new paradigm. I mean, but okay, so that accretion is actually one of the main drivers for galaxy evolution, where the mode of star-forming galaxy is relatively universal. Now, of course, that doesn't resolve everything, and we have a lot of questions. And again, I mean, now you want to understand more and more, and so you want to go more into the principal decomposition. And so I will list a lot of questions that I have, and there are many more. So, I mean, of course, we still don't know what drives the structural evolution of galaxies, and I will go that's related to your question. We know that the dispersion of the main sequence is actually a physical dispersion. So it's not led by our inability to measure the star formation rate. Okay, so we believe that the 0.3 dex encompass some, if you take the power spectrum of the star formation history of galaxy, in a sense, it should explain the 0.3 dex. So you have information that is not yet very exploited into the dispersion of this main sequence. We don't know much about the role of environment because most of the measurements that I show you are very small field that basically contain maybe one structure at a given redshift, but that's it. And so we still don't know much, and it should be an effect of the environment. I didn't speak too much about the major merger, but they most likely have a role, and likely with the structural evolution, and likely with the formation of this red and dead elliptical, because to form this elliptical, the classic scenario is that you have the merger of two spirals that come with their own angular momentum, and then you mix this angular momentum to create this non-rotationally support system. And then all I showed is basically stop at z=4 because most of the things that I showed are relying mostly on far infrared and submillimeter, millimeter observation that are hard to probe a much higher redshift because galaxies are becoming quite faint. I mean, for Herschel, it was really impossible. Okay, so I will not go through all this question, but I will try to show you 3 different ways that we have been pursued over the last years. Try to give some beginning of answer, small beginning of answer of this question. Okay, so the first thing is what drives the structural evolution of star-forming galaxies. So as you ask, indeed, we know from Hubble, I mean, the F160 observation from Hubble were enabling us to measure the optical, so the stellar component of galaxies, of star-forming galaxy, and of quiescent galaxy up to the redshift again, 2 to 3, very nicely. And we know that there is what we call a mass-size relation. So that means that galaxies, as they evolve in mass, they get a bit larger. And so that's involved that if you connect, I mean, you have to be careful, but yeah, you have to connect a descendant and progenitor. But that means that when they grow, when they grow in mass, they have to grow in size also. And also, you can see that the quiescent galaxies are way smaller, way more compact. And therefore, whatever the mechanism that turn star-forming galaxy to a quiescent galaxy, it must involve a very significant phase of compaction. Okay. So this is the diagnostic that you get from Hubble. But of course, if you want to understand, I mean, so then there's model. So usually people are saying, okay, you have inside-out growth. Okay, so that means you deposit a bit more of star formation in the outskirts, and that's how you grow. And you can have also angular momentum redistribution, but you can have inside-out growth. And here they usually invoke white and dry compaction. Okay, so I mean, to try to verify this, what you need is to measure the star formation distribution into this galaxy. But with Herschel, no way. I mean, those galaxies, what I showed you before, it's blobology. So I mean, Herschel is just a blob. So you don't resolve this. With ALMA, you can do that, but you can do that for few galaxies. It's very expensive with ALMA to do this far infrared morphology. So what can come to the rescue is James Webb. I mean, it's a fantastic machine, and everyone is using a lot NIRCam and NIRSPEC. But MIRI is also on board, and it can give you a lot of information about the mid-infrared emission, the same way Spitzer was giving us the 24 micron flux of this galaxy. And the 24 micron at up to redshift of 2 is actually a very good probe of the star formation activities of a galaxy. Okay, so with MIRI at 21 micron, we can, not a very high resolution, but you have a resolution of 0.5 arcsecond, so you can start resolving this galaxy. And so that's what we have been trying to do with MIRI observation, and then you can do that for thousands of galaxies, not for 10 galaxies as you can do with ALMA. And so here is a work that was published by a student not a long time ago, where we compare the position angle, the size, and the CRC index of the stellar component. And here on this side of the star-forming component. So where does star formation happen in those galaxies? And so rapidly, if you see, we find that the star-forming and the stellar component are actually looking very much alike. We have more or less the same CRC index. The star-forming component also have a flat B over A distribution, so that means it is organized into like a disk, okay? And this disk more or less align and overlap with the stellar component. So basically, you have star formation where the disk is. You have a CRC index that is slightly smaller than 1, which could say that you have indeed inside-out growth. Now, if you go a bit more and you try to look at some correlation, I mean, we do that a lot in this paper. Here I show you the CRC index, so the light profile of the star-forming component here and of the stellar component as a function of mass. And if you are familiar with this, you can see that the CRC index of galaxies in the optical at high mass increase a lot. And this is well known from the Hubble, okay? And this is actually Hubble observation here. And it's because as you go to higher mass, it's known that you have the star forming, you have still the stellar disk, but you also have a bulge that become more and more dominant. And so as you go to higher mass, since you do only one component CRC index, I mean, you start to be in between. And so that's how it looks like. But you can see that the star forming component doesn't do that at all. So in a sense, what we see is that at all stellar mass, the star formation happens in a disk, but it doesn't happen in the bulge at all, or it doesn't have a bulgy morphology. So in a sense, we see the inside-out growth of the disk, but in this average mode, in this secular mode, in this secular phase, we don't see the formation of the bulge. Now, of course, you can look at dispersion, and so here is the average trend. So you look at the average trend, but if you, so it's a bit of a complicated plot, but okay. The only important thing is that we find a small population of galaxies for which we have an extended stellar component. But then for this 15% of galaxies, we have a very small star-forming component at the center of these galaxies. And so what we are seeing in this phase for 15%, it's kind of something that I could sketch like that, okay? And actually, if you look at the CRC index of this 15 galaxy, of the CRC index of the star-forming component, is not equal to 1, but it starts to be slightly greater than 1, as you would expect if you are looking at in situ bulge formation. And if you look at the axis ratio distribution, which tell you how three-dimensional, I mean, what is the third dimension of your object, if you have the statistic, that it look a bit like symmetric in all dimensions. So it starts to see in situ bulge formation. And we have also with the F3 Cosmos, I will not show you a Nature paper where we look at the brightest galaxy in ever observed at ALMA. And we also found that it seems that star formation can itself organize already into a bulge, which is a bit striking because normally you would expect the gas to reorganize into this very rapidly in only few million years. But we see site of star formation that seems to be already organized into a bulge. So you have in situ bulge formation and not bulge formation via the merger and the mixing of the angular momentum. Okay, so that was about the structural evolution. I hope I still have a bit of time, yes. So now we'll go, what is the origin of the red and dead elliptical? I think it's one of the big questions. So yeah, if you want to, I mean, that's okay, how you form this red and dead. And it's very striking because that means you need to change their morphology and at the same time you need to kill your star formation activity. So that's, and it seems to be, it has to happen fast because you don't have a lot of things in the green band. Okay, so I will not give you the answer of this question, unfortunately, but okay. What we can do is that with the F3 Cosmos, if we can measure the gas for this galaxy, we can try to measure the gas for this galaxy. And at least answer whether or not this galaxy have been quenched because, in a sense, the gas is not there. And so they are not forming stars because they don't have molecular gas or they have molecular gas, but they lost their ability to turn this gas into stars. And so that's what we have been doing. It's a paper that is submitted and will soon be hopefully accepted. I mean, it's minor revision, so that should be okay. So yeah, I show you the gas fraction of galaxy as a function of redshift, and this is our good old main sequence galaxy. Okay, so that's the increase of the gas fraction for a galaxy at a given mass. And here I show you the stacking that we have been doing with F3 Cosmos that led to non-detection. So I don't show you the stamp, but there is no detection. Okay, and so you can see that it's about a factor 10 lower than main sequence galaxy of the same mass. And in this exercise, what we do also is that we could classify the galaxy in terms of time since quenching. Okay, it's a bit tricky, of course. You have to trust your star formation history derivation. But what we found is that the gas is not anymore in this quench galaxy, even right after the quenching event. So, and so it seems to support a gas removal scenario acting on very short time scale. Okay. And so that's the kind of work we can do, and hopefully we can do better because I mean the database is increasing, and so in a few years we can press the button and redo the same paper, and hopefully at this kind of constraint. So of course other people have been doing it. Here I show you some individual data points, but of course it's few galaxies, so you never know if it's maybe this galaxy or not. So here we are stacking like hundreds of stuff of Poisson galaxy on a mass complete sample of Poisson galaxy. And so now I will finish on what's happened at z=4. Okay, so if we try to push this to the highest redshift, so as I said, we couldn't do it because basically Herschel can not detect much at a redshift greater than 3. Okay, because of the selection function, you are. It was great to see the peak, but as soon as the peak is redshifted away, I mean, then you are devoid of many photons. So, but so what we can do is again use the FreeCosmos database. So now you have thousands of galaxies into it. We had to develop a full system to kind of blind our database because you can imagine we have targeted observation, so it's not a blind survey. So you can only use the part that is not at the space center. So you have to use only the serendipitous detection. You have to be careful that the clustering of galaxies did not affect. But if you assume that galaxies are Poissonally distributed, you can use this surrounding area of your target to start to do like you will do for a blind survey with what we were doing with Herschel, but with this database. Okay, and you can only do that with this database because if you need thousands of galaxies to do that. So this is the work that was done by Alberto. Using the FreeCosmos database, and here I show you the star formation rate density of the universe that we derive. And so you can see that we can push with better statistic what was happened at redshift greater than 3, which was the limit from Herschel. And what we found is that what people have been inferring from the UV corrected from dust attenuation is not totally bad. Okay, so there were some very Herschel, very optimistic for the far infrared community, star formation rate density that was about a factor 10 higher than that. But at the end of the day, we find something that is very close to what was expected from the extrapolation from the UV. And we can also do that for the star formation rate, the cosmic dust mass density. And again, it's a work by Alberto where we can see the decrease of the dust content of the universe. So this decrease is very important because somehow when you can push it, and if we are able to push it even further, that constrains a lot the mechanism that are at play to create this dust. Because as you know, the dust can be mostly produced by AGB or a supernova. AGB takes 1 or 2 gigayears to take place. And so if you have a lot of dust in the first gigayears of the universe, that means that you need supernova or ISM growth of the dust. Okay, and so the even highest redshift, I like to show this result that was led by Lord Sala, where we start to look at the main sequence. So it's very difficult, of course, at the highest redshift because again you have only you don't have the far infrared, but okay, you rely on the star formation rate from the UV. And what we found is that the main sequence is in place already at redshift 6, 7, and there is tentative evidence that the dispersion of this main sequence start to explode at a redshift greater than 7. Okay, where we will say it's a transition from a stochastic mode of star formation activity to a more secular mode of star formation. But I think it's still quite a bit of work to do here because you need more data, and of course part of the dispersion is due to the measurement error. So this is still relatively preliminary result. Okay, so I think I will stop here. With all these conclusions. So I mean, I hope I convince you that I mean, galaxy evolution seems to happen mostly in a universal mode of star formation activities, up at least to redshift of 4, that is mostly driven or controlled by the ability of a given halo of a given mass at a given redshift to accrete gas from the cosmic web or from its CGM. And of course, we have a lot of questions, but you have a lot of facilities that will come. I mean, the environment with Euclid. I mean, James Webb can push it to the highest redshift. And of course, you have Prima that will give us a new view on the far infrared, hopefully, of galaxies. You have SKA that will come. There is CCAT-prime that will give us also more knowledge on at the highest redshift on the far infrared. And you might not know about this antenna. It's a project of a 50-meter antenna that is named AtLAST, and that we will like to put on the ALMA plateau at the horizon of 2040 in this ESO New Horizon call. And that will basically give you a full census of the far infrared and the cold molecular phase of the universe up to redshift of 8 or even beyond. Okay, thanks a lot.
Thank you, Benjamin. Perfect timing also. We have time for questions. People here